For this one, it asks us to solve each of these, and you can either solve by factoring, completing the square, or the quadratic formula. Always check for factoring first, so here I build a bridge. That's a negative 10. Two numbers that multiply to negative 10 to add to a negative 3 is a negative 5 and a positive 2. If you can come up with those two numbers, it means that this thing can be factored. So now that's going to factor into an x minus 5 and an x plus 2. And now for solving, I just set each factor equal to 0. And this gives me two pretty simple equations to solve. Here I add the 5 to each side, so I find out that x equals 5. Here I subtract the 2 from each side, so I find out that x equals a negative 2. In number 18, we once again start off to see if this thing's going to factor. I build a bridge. That's a negative 12. Two numbers that multiply to a negative 12 but add to a positive 1 are a positive 4 and a negative 3. This one I can't use my shortcut on like I did with the last one. I can't go right to the factors because there's a 3 out front. So what I'm going to do is I'm going to split up the middle term and factor by grouping. So I split up this middle term. I'm going to rewrite it as 3x squared plus 4x minus 3x minus 4. So I split that middle term up, and then I factor by grouping. So I group the first two terms together. I group the second two terms together. I have the first two terms, I can factor out an x, leaves me with a 3x plus 4. I have the second two terms, I can factor out a negative 1, leaves me with a 3x plus 4. So my two factors now are the 3x plus 4 and the x minus 1. So now this thing is factored, but keep in mind, this thing was equal to 0 the whole time. So now I set each factor equal to 0. Let me take that over here just a little bit. I do the 3x plus 4 equals 0, and I solve. And then I also do the x minus 1 equals 0 and solve. So I get these two answers. I get the x equals a negative 4/3, and I get the x equals 1. Okay? Number 19, again, I might start off building a bridge. Two numbers that multiply to a negative 8 but add to a positive 3. It's not going to happen. This one can't be factored. So then I either do completing the square of the quadratic formula. For completing the square, I want an a value that's 1 and a b value that's even. I don't have a b value that's even here, so I'm going to go to the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And I just start plugging in what I know. I know the opposite of b, that's a negative 3 plus or minus the square root of 3 squared minus 4 times a, which is 1, times c, which is a negative 8, all over 2 times 1. That's a negative 3 plus or minus the square root of 9 plus 32 over 2, which is a negative 3 plus or minus the square root of 41 over 2. And there's not really anything else I can do with that. There aren't any perfect squares that divide evenly into the 41, so I'm going to leave that exactly the way it is. Okay? In the next one, this one also can't be factored. I can try building a bridge and coming up with a negative 10 and two numbers that multiply to negative 10 to add to a positive 2, but it's simply not going to happen. So I'm going to go to the completing the square on this one, since I have an a value that's 1 and a b value right here that's even. Just to show you completing the square. Quadratic formula will work just fine on this one, but what I'm going to do is I'm going to add this 5 to each side. So I start off by adding the 5. That gives me an x squared plus 2x with a little blank space equals 5. I'm creating space, and now I complete the square, which is where I take the b value, divide it by 2, and square it. If I take that off to the side, that's 2 divided by 2 squared, which is 1 squared, which is 1. Okay, so that's what I fill in this blank. I put a plus 1 here. Whatever I do on one side, I have to do to the other side. Okay? This side is going to factor into an x plus 1 squared if I build a bridge and factor it, equal to a 6. And now I can simply solve using my square root property. So I take the square root of each side. So I take the square root of each of these. That gives me an x plus 1 equals plus or minus the square root of 6. Remember, whenever we take the square root of each side, we've got to do the plus or minus. And then I subtract the 1 from each side. So I find out that x equals a negative 1 plus or minus root 6. And that's it. Those are my two answers. For the next couple, we just want to list the number and type of solutions. So for this, I'm going to use the discriminant. Remember, the discriminant is b squared minus 4ac. It's the thing that's under the square root in my quadratic formula. Okay? And so if I do that with this first one, I do 6 squared minus 4 times a times c. That's going to give me a 36 minus 32, which is a 4. And remember, when I get a positive number that's a perfect square, it means that I have 2 rational solutions. Okay? And number 22, I do the same thing. I do b squared minus 4ac. I simplify, that's going to be a 16 minus 16, which is 0. When I get a 0 for the discriminant, it means I have 1 rational solution. And now if I apply the same thing to the last one, I do the b squared minus 4ac. That's going to give me a 9 minus 20, which is a negative 11. When I get a negative value under that square root, it means I have 2 complex solutions. And now number 24 is kind of asking me to look back and say, okay, what am I missing? What's not present up here? I've got 2 rational, 1 rational, and 2 complex solutions. The only other option here would be to have 2 irrational solutions. And we get 2 irrational solutions when the discriminant is a positive that's not a perfect square. And an example of that would be something like, I don't know, 23. Why not? Okay. On number 25, we're asked to find the vertex and the x-intercept of the quadratic equation, and then interpret what this means. All right. So let's find the vertex first. To find the vertex, I have to do the opposite of b over 2a. So that's going to be a negative 4 over 2 times 1, which is a negative 4 over 2, which is a negative 2. And that's the x value for my vertex. Okay, so the x value for my vertex is a negative 2. To find the y value for my vertex, so my vertex here is a negative 2 comma something, I have to plug that negative 2 back in. So I plug the negative 2 back into my equation. This is the process I go through for finding the vertex. That gives me a 4 minus 8 plus 4, which is 0. So my vertex is negative 2, 0. It also asks me to find the x-intercepts. The x-intercepts is when y equals 0. So essentially, I set this equation equal to 0, and I'm going to solve it. So I build a bridge, and I factor it. 2 numbers that multiply together to give me a 4, but add to a 4 is a 2 and a 2. That means this factors into an x plus 2 and an x plus 2. I set each factor equal to 0, and really, since it's the same factor twice, I just need to do it once. I'm going to get the same answer both times. So I find out that x equals a negative 2. All right? And really, that's significant because when we think about this guy as an ordered pair, I got a negative 2 for x, and I had plugged a 0 in for y. And when we look, this is the case where my x-intercept and my vertex are the same thing. All right? In other words, what's significant here in terms of interpreting these is if I were to graph this parabola, the vertex is back here at negative 2, but that's also my y-intercept. It's a parabola that just touches the x-axis. Okay? And that leads us to an interesting discussion about the vertex versus the x-intercepts at times, and also deals with multiplicity, which we'll get into a little bit later. Okay? For this one, it asks me to simplify each expression. So this one, I'm just going to multiply this out. So I'm going to distribute. So I distribute the 2x to each of these. When I distribute the 2x, that gives me a 2x cubed plus 4x squared minus 8x. Then I distribute the 1. That gives me an x squared plus 2x minus 4. And now I just combine like terms, which I have a couple of them. So that leaves me with a 2x cubed plus 5x squared minus 6x minus 4. That's it. For this one, it asks me to square this thing, and if I want to square this thing, 4x plus 5 squared means I have 4x plus 5 times 4x plus 5. I have to write it out this way because I have to distribute. Don't just square each piece. When I distribute the 4x, that gives me a 16x squared plus 20x. When I distribute the 5, that gives me a 20x plus 25. And if you just square each piece, you're going to end up with the first term and the last term. You're not going to have the middle term, which means you're not going to have the entire answer, which is this guy. Okay? For the next one, it asks me to divide the polynomials. For this one, I can either use long division or synthetic division for this one. And really, synthetic division is typically the way we want to go. I want to take the opposite of this thing because I'm basically testing the solution. If I were to set x, I'm going to put a -3 in the box. And the reason for that, again, is because if I were to do x plus 3 equals 0 and solve this, I'd find out that x equals a -3. That's what I'm plugging in when I do synthetic division. So now I write down my coefficients in descending order. So here I've got a 1, here I've got a -10, and here I've got a 7. But the issue here is I'm missing the x squared, so I've got to put a 0 in its place. So I do 1, 0, -10, 7. And now I bring down the first term. I multiply what's in the box times what's underneath. That's a -3. I add straight down. I multiply what's in the box times what's underneath. That's a 9. I add straight down. I multiply what's in the box times what's underneath. I add straight down. And now from here, I just want to interpret this thing. Since I started with an x cubed, I divided by an x to the first. Means my answer starts with an x squared. This is a 1x squared minus 3x minus 1. And then this 10 is my remainder, so I put a plus 10 over the thing I was dividing by, which was the x plus 3. Okay? For number 29, I can use long division or synthetic division. To use synthetic division, however, I can't use synthetic division if there's something other than a 1 out front, so I have to turn that into a 1. So what I do is I divide each of these pieces by 3. And essentially, since this is division, it's like I'm dividing the numerator and denominator of a fraction by 3, which is fine because it's like multiplying by 1/3 over 1/3, okay? I'm not changing, I'm just changing the way it looks. So I'm changing it to this problem, a 2t cubed plus 5/3 t squared minus 2/3 t plus 1/3 divided by a t plus 1/3. So now I put a -1/3 in my box. I write down my coefficients in descending order, the 2, the 5/3, the -2/3, and the 1/3. Doesn't look like I'm missing any terms. I bring down the first value, that's a 2. I multiply, that's a -2/3. I add straight down, that's a 3/3, which is a 1. I multiply, that's a -1/3. I add straight down, which is a -3/3, which is a -1. I multiply, that's a positive 1/3. I add straight down, that's a 2/3. And now to interpret this answer, it looks like this. It's telling me that I have a 2t squared plus t minus 1 with a remainder of 2/3, which I would put the 2/3 over the thing I was dividing by. And there's one last little trick here. I can't leave it like this. When I look at that remainder, I've got a fraction over something that's got another fraction, and that's just not acceptable. So I'm going to multiply that remainder. Let me take it off to the side here. 2/3 over t plus 1/3. I'm going to multiply that remainder by 3 over 3. I'm essentially going to change the denominator to try to get rid of these fractions. In the numerator, when I multiply that, it gives me a 2. In the denominator, I have to distribute the 3, which gives me a 3t plus 1. And you notice what happens is I'm back to the thing that I was dividing by from the original problem. So my final answer is a 2t squared plus t minus 1 plus 2 over the 3t plus 1. And if you use long division, you should come up with the same thing. Okay?